Hello friends, today we'll continue with next case of problem in design of beams. Let us note down the problem. A roof of a hall measuring 7 meters by 14 meters consists of 120 mm RCC slab supported on I section. I section, this is the member which you have to use. Spaced at 3.5 meters center to center. The hall is having 230 mm thick wall all around. The finishing loads, slab finishing is 1.5 kilonewtons per meter square. Live load 2 kilonewtons per meter square. Design the beam and apply all the checks. Say this is the hall. So 7 meters by 14 meters, these are internal dimensions. 14 meters, 7 meters, internal dimension in twin. Next 230 mm wall. So from here to here, this is 230, and here to here this is 230. If I have to draw the cross section, it will look like this. This is the slab walls, and thickness of the slab is 120 mm. Now how to place the beams? Very important is placement of beams. Dimensions are given as 7 meters by 4 meters. Always beams have to be placed parallel to shorter span, and spacing is given as 3.5 meters center to center. So what you do is, this is the shorter span, place the beams parallel to shorter span. From here 3.5 meters, from here center to again 3.5 meters, from here again 3.5 meters. So this I section I am going to show it like this here. The top flange is embedded in the slab. This dimension from center till here, center of this beam to inside. So these dimensions are 3.5 meters. Now I have to find out what is the load taken on each of the beams. So for that, mark the center of this, this much is the load taken by this beam. Since this 3.5, this dimension will be again 3.5 meters. So this much load is taken by this beam. So let us start with the load calculations. Load calculation. So I have to calculate what is the UDL generated on this beam. So first, dead load of slab. So dead load of slab, thickness 0.12, width 1 meter. I am going to consider 1 meter width into 1 into spacing 3.5 meters into unit weight. So this gives me the answer 10.5 kilonewtons per meter. Floor finish. So floor finish is given as 1.5 into 3.5 meters center to center spacing. So this gives me the value 5.25. Live load. So live load is given as 2 kilonewtons per meter square into 3.5 meters center to center spacing. So this gives me the answer 7.0. Dead load of beam, that is self weight. Assume. This is assumed value. So usual typical value is 1.00 kilonewtons per meter. So these are the loads. W 23.75 kilonewtons per meter. Calculate factored load WU 1.5 into W, that gives the answer 35.63 kilonewtons per meter. Next, we have to calculate now shear force and bending moment. I have to calculate shear force and bending moment for factored load. WU is equal to 35.63. Next, first step, I have to calculate effective length. Effective length of this beam, and effective length of this beam is given as center to center distance. Effective length LE is equal to center to center distance, and that is given by 7 plus 0.23 wall width half plus half. If nothing is given wall width, you can assume it as 0.23. So LE is equal to 7.23 meters. Next, bending moment MU is, for simply supported beam, WL square by 8. So 35.6 into 7.23 square divided by 8. So this gives me the value 232.81 kilonewton meters. Similar VU, or later on terms we'll be using it as V. VU is WL by 2, and that gives me the value 128.8 kilonewtons. So these are the values for which you have to design the I section. Now once loads are calculated, I have to start with the trial section. So step 2, trial section. Calculate required plastic modulus ZP using design moment equation. So this is the equation available in the code. MD is equal to beta B ZP Fy by gamma m naught. This is available in page 63. I have to design for plastic sections. Hence, beta B is equal to 1 for plastic sections. So I know value of MD. MD is nothing but M, 232.8 into 10 raised to 6 newtons mm is equal to beta B is 1, ZP is required into Fy 250, gamma m naught 1.1. So solving this, I get ZP is equal to 1024.36 into 10 raised to 6 mm cube, or same I can write as 1024.36 centimeter cube. So this is the required plastic modulus. Increase by 30%. This is an approximate value so that all the checks are passed. Therefore, ZP required is equal to 1204.36 into 1.3, 30%. So I get the value 1331.6 centimeter cube. This much ZP is required. Now choosing the section, you have to refer to IS 800. So refer page 138. From page 138, select a section such that its ZP is little more than this value. So try ISLB 450 at 65.3 kg per meter. This is a section I have chosen and I am going to try it, and its ZP is 1401.3 centimeter cube. Now refer to these values in steel table and write the values from steel table. Flange width B is equal to 170 mm, height H is equal to 450, thickness of flange TF 13.4, thickness of web TW 8.6, radius at root R1 16 mm. So these are the values we get from steel table. Next, ZE is equal to ZXX is equal to 1223.8 centimeter cube. So these are the values which we require later on. Next step, step 3, check for section. Check for section means you have to verify whether that section is plastic. Now to check for section, refer to table 7. Check for section, refer table 7. In that these values are given and even this diagram is given. For this diagram, this is height h, this is thickness of web, thickness of flange. Now IS 800 defines B as half the flange width. So this is B here. Now height D is this value. This value is radius at root R1. Again you get all these values from steel table. Now this dimension D is defined as D is equal to H minus 2 times TF minus 2 times R. 2 into TF minus 2 into R1. This is the definition of D. Now from table 17, I have the equation B by TF. This equation. So B is 170 divided by 2. This overall dimension from here to here is 170 and this B is half of that. So 170 divided by 2, thickness of flange TF 13.4 and this is given by 6.34 and this should be less than 9.4 epsilon. Epsilon is always 1. Next, D by TW. So D is H 450 minus 2 into TF thickness of flange 13.4 minus 2 into thickness of radius at root R1 divided by TW 8.6. So you have the value 45.48 which is less than 84 epsilon. Hence okay. The section is plastic. This is the meaning of it. Now fourth step, step 4, check for shear capacity of the section chosen. Now I have the values V is equal to VU, that is factored shear force 128.8 kilonewtons. Design shear stress VD is given by AV into FYW root 3 by gamma m naught. And this equation is available on page 59 of codebook. Now substitute the values, get the value of VD. For that you need to calculate AV and AV is area in shear. And area in shear is this total area. From here to here, and this area in shear is given by TW into H. Area in shear is equal to H into TW. So H is 450, TW is 8.6. Now I have to calculate VD. So VD is equal to 450 into 8.6 FYW. So FYW is nothing but yield stress of steel, that is FY 250 divided by root 3 into 1.1. So this gives me the value 507 kilonewtons, which is greater than 128.8 kilonewtons. Hence it is safe in shear. Step 5, check for moment carrying capacity. Check for moment capacity. Before you start for moment carrying capacity, you need to determine whether V is greater than 0.6 VD or less than 0.6 VD. For that, refer page 59. There are separate equations, so we have to check those equations. First, calculate 0.6 into VD. So 0.6 into VD Moment carrying capacity 507 kilonewtons. Already I calculated it here. So this gives me the value 304.2 kilonewtons. Now compare this with V. So shear on the section is 128.8 kilonewtons. So I have to compare 0.6 VD and V. So I get the equation V is less than 0.6 VD. When V is 0.6 VD, refer clause 8.2.1.2, page 53. Page 53. So it gives the equation moment capacity is equal to md is equal to beta b zp fy by gamma m naught, and this should be less than or equal to 1.2 ze into fy by gamma m naught. So substitute the values. md is equal to beta b is 1 for plastic sections, zp 1401, this is the value for the chosen section, into 10 raised to 3 centimeter mm cube, into fy 250, gamma m naught 1.1. this should be less than or equal to 1.2 into ze. Ze is 1223.8 into 10 raised to 3 mm cube, fy 250 divided by gamma m naught 1.1. So I get the value 318.4 into 10 raised to 6 Newton mm, and this is less than or equal to 333.7 into 10 raised to 6 Newton mm. So this satisfies this condition. Hence moment carrying capacity md is 318.4 into 10 raised to 6 Newton mm, or I can say 318.4 kilonewton meters, and this is greater than moment. So moment on this section is 232.8 kilonewtons meters. Hence safe in moment. Now let us do the check for deflection. Next step, step 6, check for deflection. For this, refer to table 6, page 31. Permissible deflection or maximum deflection is given by span divided by 300. So span is nothing but effective length 7230 divided by 300. So this gives me the value 24.1 mm. So this is the permissible or maximum deflection. Actual deflection is given by, for simply supported beam, 5 by 384 WL raised to 4 by E into IX. So 5 by 384 W factored load 35.63 into 10 raised to 3. What this is in kilonewtons, convert that into newtons. WL raised to 4 effective length 7230 raised to 4 divided by E Young's modulus for steel 2 into 10 raised to 5. I value, it is taken from the steel tables, 27536 into 10 raised to 4. This is in mm raised to 4. So I get the value 23.01 mm. So I have to compare this value and this. Actual should be less than permissible. Hence less than 24.01. Hence safe in deflection. So next step will be step 7. Check for web crippling. Check for web crippling. So for this, refer page 67, clause 8.7.4. Check for web crippling. Say this is an I section, top flange, bottom flange. This is a cross section. Because of heavy loads at its support, it may cripple, the web may cripple like this effect is called as web crippling, and this height is given by h2, and that h2 height is available from the code books, this height, and code gives the reference as the web crippling height is at a slope of 1 is to 2.5 from the edge of the support. So this slope is 1 is to 2.5. So this distance, I have to calculate these distances. This distance is nothing but b1. b1 is support width. Let this distance be n2, and this height is h2. h2 value you get from the code books. So from steel tables, h2 is equal to 33 mm. So this is for ISLB 450. Next, n2. This height is given by 2.5 into h2. 2.5 into h2. So 2.5 into 33, I get the value 82.5 mm. B1 is nothing but bearing width or support width. Bearing or support width. Whatever width of the wall you assume, that value is to be taken as B1. Web crippling equation is given here. Fw is equal to B1 plus N2 TW Fyw gamma m naught. 8.7.4 page 67. Where B1 is bearing width 230, N2 I have got that, TW thickness of the web, Fyw yield stress of the web. So Fyw is nothing but Fy. So substitute the values here. So bearing width 230 plus N2 82.5 into TW 8.6, Fyw is nothing but Fy 250 divided by 1.1. So solving all this, I get the answer 610.7 kilonewtons, and this is greater than 128 kilonewtons. This is the shear force Vu. Hence, okay or safe in web crippling. Next check will be check for web buckling. Check for web buckling. That is given by equation 8.7.3.1 page 67. Let us go here. Page 67. Web check. Web buckling. The area of cross section is taken as B1 into N1 into TW. So this is the area supporting the web buckling, where B1 is width of the bearing, N1 is dispersion, and if I have to draw the longitudinal view, say this is the I section, top flange, bottom flange, this is the support, this much is the support width, that support width is indicated as B1. Now maximum buckling occurs at the center if this is the height h. Maximum buckling occurs at height h by 2. And for web buckling, dispersion line, load distribution line is at 45 degrees from this edge. If this is h by 2, this value is indicated by n1. So let us write those values. B1 support width 230 mm, N1, and that is nothing but h by 2. So h is 450 divided by 2, I get the value 225. Now according to clause 8.7.3.1, capacity of web. Capacity of web FCDW. Direct equation is not given, only area is given. that area divided by FCD gives me the capacity. So area is given by equation B1 plus N1 into TW by FCD, where FCD depends on slenderness ratio, and slenderness ratio lambda is given by 2.45 D by TW. Now here D is this value. This is the D. This is TF, and D is given by H minus 2 into TF minus 2 into R1. TF and R1 you get from steel tables for ISH with 450. So H is 450 minus 2 into 13.4 thickness of flange minus 2 into R1 16. So solving this you have the answer 391.2. Therefore lambda is equal to 2.45 into 391.2 divided by 8.6. So you have the answer 111.4, and Fy is 250. Now refer table 9C. Refer table 9C. From table 9C, I have the values for 110 and 120, 94.6, 83.7. I have to interpolate for 111.44. So for interpolation, I get the value FCD is equal to 93 MPa. Now get the value of FCDW, web buckling capacity. So 230 plus 225 into TW 8.6 into FCD. FCD is 93. So I get the value 364 kilonewtons, which is greater than 128. That is VU. Hence, safe in web buckling. This completes the problem. Thank you.